Hi everyone, today at the seminar we are hosting Jakub Tarnawski. Please start.
All right, thank you. Thank you very much for having me, and thanks everyone for coming. So I want to talk about algorithms for scheduling, namely for minimization of Makespan under precedence constraints and also under communication delay constraints. And these algorithms are based on LP hierarchies. So this is a joint work with Janardhan Kulkarni, we are at MSR, and with Shidi and Minwei, who are at the University of Buffalo. Okay. So the problem is well known. You have n jobs, and the jobs can have different processing times, or that we also call sizes. They are denoted by pj. So we usually have this drawing of a rectangle, and then the width of the rectangle is the processing time of the job. Okay, and the problem is to schedule these jobs on m identical machines, such that the precedence constraints are satisfied. So we also have a partial order or a DAG equivalently that gives the precedence constraints. Okay, so let's say you have two identical machines, then a feasible schedule could be like this. Okay, so precedence constraint going from job 1 to job 2 means that you cannot start job 2 until job 1 has finished executing. Okay. So the time at which everything is done is called the Makespan, and this is the objective function that we want to minimize. And the main question here is, what is the approximability of this problem? Okay. So already in 1966, Graham gave a two approximation to this problem. It can be known under the names of least scheduling or just greedy. And really, you can think that every reasonable algorithm proceeds somehow like this. Okay, so whenever you have a machine that's idle, you just take any job that's available and run it. Okay, so then let's say this is an example instance, and then if you have two identical machines, then what the algorithm could do is maybe take job number 1, schedule it here, and then you have one more machine that's idle, and you can schedule job 2. And after that, you can start maybe job 3. Job 4 is also free, so you can run it. And then you have to wait until job 5 becomes available, and so you get this schedule. So this schedule is feasible. It's a two approximation. It's not optimal. Like optimally, you would start with job 3. Okay. And the analysis of this, which I will show you, says that the Makespan can be actually bounded by opt plus the maximum length of a chain in the input, which is also a lower bound on opt. So in total, you get 2 times opt. Okay, so then it's a familiar situation. You have some trivial algorithm from the 60s or 70s, and it seems really hard to beat. It's a major open question in scheduling theory to get better than two approximation. In 78, Lenstra and Rino showed an NP harness of 4/3 approximation. And then there is a result by Svensson from 2010 that under a variant of the unique games conjecture, it's actually hard to get better than 2. And this holds even for the important special case of unit sizes. Okay, and so this is going to be hard to beat unless you're going to refute this variant of the UGC. But there is a very relevant and important special case, which is when the number of machines is a constant. And this is what people have looked at. And actually, in practice, this is quite okay to make this assumption a lot of the time. So for instance, nowadays we have this problem of scheduling neural networks, and often the setting is such that you have a machine with maybe like 4 GPUs, and you want to partition the network to run it. and so then M would be 4, for instance. So this is actually quite relevant, and this will be our setting for the rest of the talk. Okay, so the number of machines M is some constant; it's bounded. Okay, so if M is bounded, then this is what we know. Okay, so first let's look at the special case where jobs have unit sizes. Okay, so then if you have 2 machines, the problem is in P. This is known since the 60s. There are multiple quite different algorithms that solve it in P. But then as soon as you get 3 machines, we basically don't know a lot. There's a 4/3 approximation, but we actually don't know whether the problem is even NP hard. This is a major open question. It's actually one of the few still remaining open questions from the book by Gary and Johnson about NP completeness. Also, it's not known, but it's conjectured that there is a PTAS for 3 machines, or even for any constant number of machines. So like we don't know whether it's NP hard for 100 machines even, and we don't know a PTAS even for 3 machines. And for arbitrary sizes, well, if you analyze Graham's algorithm a little bit more precisely, then you can say it's a 2 minus 1 over M approximation. And it is strongly NP hard. In fact, it's NP hard even for jobs of sizes 1 and 2. Okay, so this 2 minus 1 over M has been slightly improved by Gangal and Ranade, but like basically asymptotically, it's still a 2 approximation. Okay, so then there was a breakthrough result by Levey and Rothvoss in 2016 for the unit size case. So they gave almost a quasi-polynomial time approximation scheme. So this almost QPTAS is the following. So again, the setting is unit sizes. So the length processing time of every job is 1. So they used a natural LP. So there is a natural LP for the problem. The issue is that it's not that useful in of itself because its integrality gap is 2. What they do is they take the Lasserre hierarchy and they lift LP to almost polylog many levels of it. And then they use this lift to get a 1 plus epsilon approximation by rounding this LP solution. So the running time of that algorithm is dominated by solving this large lifted relaxation. So it's n to the O of R. That's like almost quasi-polynomial. And Shashwat Garg in 2017 then showed that actually it's enough to have like really polylog many levels of the hierarchy, and that gives you a true QPTAS. Okay.
Can you tell us what is Lasserre hierarchy?
Yes, there will be something about this. Yeah. All right. Okay, and so in this work, they actually ask, can a similar approach give a 1 plus epsilon approximation if the processing times are arbitrary, so not unit sizes? Okay, so this is the question that we try to address in this work. So it's not so clear what that actually means. So there are different ways to understand this. Actually, there are 3 possible settings that you can consider. The first setting is a fully preemptive setting. So if you have a long job, like look at this green job here, then you can process it a little bit, then process it a bit more, maybe on some other machine even, and then you go back to that machine and finish processing it. Okay, that's the most permissive model. The second setting is the preemptive but non-migratory setting, where you can preempt a job and then do something else in the meantime and then go back to processing that green job, but you cannot migrate it on another machine. Then the third setting, probably the most classic and also the most restrictive, is where this green job has to be executed in one piece. Okay, that's the non-preemptive setting. Okay. And in fact, the optimum makespans for these can be a constant factor away from each other. So you cannot hope to have a black box reduction that like only loses a factor 1 plus epsilon. Okay, so seems like we need different solutions for this. And the question is, can Levey-Rothvoss, their approach can be generalized to these settings? Okay, so for the first one, it's rather simple. Basically, what you can do here is you can take any job. Let's say you have a job of length 5, and you can just partition it into this chain of 5 little jobs. So now you have a unit size instance. You solve this, and then you will get a schedule that looks like this. Okay, like it might migrate, it might get preempted, but if we allow that, then this is fine. And you will lose basically a 1 plus epsilon factor on this reduction if like the job sizes are fractional or really large or something. But overall, it's simple. Okay. So for the second setting, which is preemptive but non-migratory, so this is the main result of this work. We show that, yes, indeed, in that setting, we can get an almost cubitas and extend their framework. And then for the third setting, which is the non-preemptive setting, we give some evidence that the lifted LP for that setting might be too weak, even for the case of 2 machines. So in particular, we show that basically the most natural approach to generalizing that framework would not get a 1 plus epsilon approximation. Okay, and one other thing that we also address is the setting of communication delays. So this is the following thing. If you have 2 jobs, J and J prime, that have a precedence constraint, if they are scheduled on different machines, then you need to wait some amount of time between the finish of the first job and the start of the second one. Okay, so if you have 2 jobs and you process them on the same machine, it's fine. You can start processing J prime immediately. But if you have them on different machines, then you need to wait for CJJ prime time. And you can do other stuff in the meanwhile. It's just that there has to be this data transfer going in the background. Okay. So this again is a model that's really relevant to practice because like you actually do need to consider these communication constraints when you're partitioning or when you're scheduling things. But from a theory perspective, we never understood it very well. Basically, there have been only trivial approximation ratios or harness results. Banzal in his survey says that it's not understood at all. Like part of the reason is that there have been no good LPSDP relaxations known for this problem. But some result that I can list is by Hannen and Muniar. They give a 7/3 approximation, but that's for a really special case because there's unit size jobs and delays are the same as the size of the jobs, which is 1. Okay, so our result is that our almost cubitas still extends to this setting as long as the communication delays are bounded. Okay, so the processing times can be large, but the communication delays should be at most some constant. And this we can do again in the same setting as the main result, which is for the setting of arbitrary sizes and the preemptive but non-migratory setting. Okay. Yes, so in this talk I will focus on our main result, which is again this almost cubitas for the preemptive but non-migratory setting. I will not talk more about communication delays. Okay, so in the rest of the talk, I want to describe to you, explain at a very high level the framework of Levey and Rothvoss, and then say what the challenges are when you get arbitrary sized jobs, and what are our new ideas in dealing with these challenges. All right. Okay, so let's begin by going back to grams to approximation. We will actually analyze it. Okay, so again, the algorithm is that whenever a machine is idle, you run any job that's available. And the way that you can bound the Makespan is by bounding it by the sum of total processing time of all jobs over m. So like this is clearly a lower bound on opt, because this is sort of what would happen if you could have all the machines processing all the time. Like any time where every machine is processing is really good. Plus the maximum length of a chain. So this is also a lower bound on opt. Okay, so why is this? This is basically because all the non-busy times in a schedule are covered with a chain. So let me show you. So let's look at the last let's look at the last time that's non-busy. Okay, so the last non-busy time is this question mark. So the question mark means, okay, why am I not processing some job? Well, because there is no job to process. Basically, I'm waiting for this job to finish, and then I will be done. Okay, that's fine. Oh, what about this time? Okay, always I look at the last time that's non-busy. So what about this time? Well, why, in particular, why couldn't I process this last job from the chain? Okay, well, this is because there must have been some other job that we have been waiting on. Indeed, maybe it's this job. Okay, fine. What about this time? Well, why didn't I process this job already here? Well, there must have been some other job that I've been waiting on. Okay, fine. What about this time? Well, why didn't I process this? Well, there must be some earlier job that I'm waiting on. Okay, so why not process this job again? Well, because I'm waiting for this job. Okay, so if I do it like this, you will see that I have covered all the non-busy times with this chain. So at all times, either I have this chain going or everything is busy. So that's basically the analysis of Graham's algorithm. So you get 2 times opt, but it's important to notice that if the longest chain were actually short, then you would get better. So in particular, this is at most opt, and if the max length of a chain is epsilon times opt, then great, then we get a 1 plus epsilon approximation. All right. And sort of one of the main ideas of Levey-Rothvoss is to use the LP hierarchy to cut those long chains. Okay. Okay. So what are these hierarchies that Przemek was asking? So there are basically automated ways to take an LP or an SDP, which is a relaxation to some integral thing that we're actually interested in, but it's hard to optimize over. And so we take such a relaxation and we raise it to some ARF level. Okay, and in this way we obtain a large, large larger in the sense of number of variables and constraints, but smaller in the sense of the polytope when you look down on the original space. So we obtain a better approximation, basically, a better smaller integrality gap, ideally. In particular, if we take R to be n, then this is exponential size, but this is actually the true polytope that we want. Okay, but we cannot take R equal to R, n equal to R equal to n, because that would be very slow. But we will take some moderate R that allows us to say something, and this relaxation can be solved in time n to the O of R. Okay, so I will actually not define any particular hierarchy because that always takes a long time and they are quite complicated. But I just use hierarchies as a black box. In particular, one property that we just extract and use a lot is this following thing, which is called conditioning. Okay, so if I have a solution X of level R, so that means the solution X of the R level lift, that has some positive weight on a variable xe. So you can think that this is sort of like a probability distribution, and it says that if this event is possible, then I can condition on this event, and I can produce some solution of one level less that actually has xe prime equal to 1, so this event always happens. Okay, and another fact that we use is that when you do this, the support of x shrinks only. Okay, so so there is no event that was impossible previously, but now is possible. Okay, so in particular,
does it mean that the solution on level R was like a mixture of the solutions on level R-1, or?
yes.
Okay.
Yes, yes. You can view it like this, yes. Yeah, so I will also not write down the LP that we use, but let me just say that we basically have the variables xjt. That means that job j should be scheduled at time t. So when I perform conditioning on this, it means that I take some job and I fix an integral slot t for it. And I can choose any slot that I want as long as the LP said it's possible to have that that job in that slot. Okay, and I pay one level to do it. All right. So clearly, if I had n levels, I could just do this repeatedly, schedule everything, but getting that sort of solution would be super expensive. Okay, so a very high-level overview of their framework is as follows. So we take the instance. They take the instance which is a DAG, and using the LP solution and some number of this conditioning operation, they partition it into a set of so-called top jobs and multiple sets of bottom jobs. Okay, like in the picture. So the top jobs have only short chains. So in this blue area here, there are only short chains. Okay. For the bottom jobs, on the other hand, we know that the support of each job here, for instance, is limited to this short interval. Okay, so I partition the time horizon between 0 to t into a lot of these small intervals. Actually, there would be many more than 4, and I have these bottom jobs that have only short intervals. Okay. All right, so the next thing that they do is they run this algorithm recursively on the bottom jobs to schedule them. Okay, so you have the machines, and then you run this recursively, and you get some schedules for every bottom interval. Okay, so now the name of the game is to add these top jobs to the schedule in some feasible way. Okay, so there are properties of the precedence constraints that allow us to do this. Okay, so let's see how the precedence constraints can be satisfied. Okay, so this depends on what jobs they go between. So for the bottom to bottom precedence constraints, they are either recursively satisfied or automatically satisfied. So what do I mean? So for these ones that are within some bottom interval, like they are recursively satisfied because this thing is a feasible solution. Okay. For these ones that go between different bottom intervals, well, they are automatically satisfied because they have to go from left to right, and we also schedule the jobs like this. So this is fine. Okay. For the top to bottom ones that are like this, like here, I don't want to go into details, but basically the gist is that these bottom intervals are so short that these are easy to satisfy. Okay, and then for the top to top, so these guys, so basically we run some list of grams algorithm now on these top jobs, and because they have short chains, my Makespan will be fine. Okay, like 1 plus epsilon approximation of some sort. Basically, I look at these jobs in the order of earliest deadline first. So deadlines are given by the precedence constraints to the bottom jobs that they have, and then doing that basically does the trick. Okay. So let me explain this first step a little bit more. So how do they partition the jobs? Okay. Oh yeah, so this arrives and then we are done. Okay, so they use this laminar partitioning scheme where we can think that these small intervals are the bottom intervals, but this is like the whole instance for now. So this is of length t over 2, this is of length t over 4, and so on. So there's this laminar tree. Okay. So there are jobs. They assign each job to the minimum interval that contains its support. So let's say you have this green job that LP tells you with extent 0.3, you schedule it here or here or here. Then the interval that you would put it in is this one. Okay. So you assign these jobs to intervals like this. Okay. Yeah, so recall that one crucial property that we wanted is that the length of chains in the top level is short. It's at most epsilon times t, and this is done by conditioning. Okay, so how does it happen? So let's say I have a long chain. This is a long chain. Okay, now I take this orange job, which is the first in the chain. Yeah, this will be like the space of top jobs. So I take this guy and I condition him to be scheduled in the very last time step where he has some support. So when I do this, he's going to go here because now his support is just a single point, so he falls down. And all these other jobs also will lose some part of their support. In particular, it used to be like this, so they were scheduled after this guy, okay, because there is a chain. So now when he gets scheduled here, they also have to be scheduled on the right. So they will no longer be in this box. They will go down to this part of the laminar partition. Okay, so this happens. And so there is some progress that is measured by how many of these jobs fall down by how much. Basically, by making a small number of conditionings, we can break up the long chains in this way. Okay. Then there are some middle jobs. There's top jobs and bottom jobs. Actually, there are also middle jobs that we somehow just discard. We don't worry about them. Okay, so they disappear. I don't want to talk more about it. And then we recurse on each of these bottom intervals. Okay, so yeah, this is what happens. We take each one and it gets some sort of schedule. Okay, and then we add the top jobs using this earliest deadline first thing. Somehow.
How many levels are there? I got lost in the math here.
Yeah, there is no math. So yeah, if someone likes math, there's a lot of math in this framework, but I'm trying to bypass all of it. So there's basically log n levels or log t levels. Yeah, and this part that constitutes the middle jobs is actually chosen so that there's few of them, and this has height like log n. If you're curious. All right, so I'm skipping all the details like this. Okay, so yeah, so what happens? So what actually costs us is discarding jobs. So these middle jobs are discarded, and I can just discard any job, and at the end I reinsert it into the correct place in the schedule on its own, like all the other machines would be idle. This costs 1, and so if I discard at most epsilon times t jobs, then it's fine. Yeah, okay, so for the middle jobs, I choose this interval of middle jobs so that there are few of them, but still the length of the bottom intervals is small. And then there is some loss in inserting the top jobs, but let me not talk about that. Okay, and the thing that we also kind of want to account for is the number of levels that we use. So this is actually really nice. I really like this point that like at the bottom of our recursion, we actually schedule everything just by conditioning. So at the end of the day, we condition on every job. but we don't have n levels to use. So this recursion really helps us. In particular, we use n conditionings, but each level of our recursion tree gets like a fresh copy of x conditioned to with the choices that we made, and then all of them are scheduled independently, which means they like get their own independent sets of levels to use. So this is quite a nice thing in my opinion, that like you condition on everything but not at the same time, and if you can preserve that independence, then you still don't have to use a lot of levels. All right. So that's what they did at a very high level. Now I want to briefly discuss what the challenges are if you have arbitrary sized jobs. Okay. So the thing that you kind of really would like to just do is take these big jobs and partition them into these small unit sized jobs. You just do that. Okay. So why don't you just do that and leave it at that? Well, you know, the problem is that then you might get a schedule that's migratory. Okay. And in particular, in this framework, if you wanted to treat these jobs as just this this chain of small jobs, then you would have to split them into multiple bottom intervals, because you know the top jobs should have short chains, so you cannot leave too many of these small jobs to be the top jobs. So most of them you have to push down, but then you have to split them into different bottom intervals. So let's say this is a super long job, then you basically have to split it into all the intervals, and then you have no control over where it actually gets scheduled. Okay, they could go to different machines. That independence that I talked about is actually kind of a curse here. Okay. So what do we do to fight this? So we have a new LP, which is also machine indexed. Okay, this is quite an easy idea that, you know, if you want to control which machine things go to, then you put it in the LP. So we have a variable x ajt, which means that a small job j gets scheduled at time t on machine I. Even though all machines are the same, we need to have this. And then we have no migration constraints, which basically say that, look, for every job, basically for every small job that comes from the same big job, you want to have the same extent of it on every machine. So what this gives you is that when you condition on one small job in this chain, you get a fixed machine for it. Like with probability 1, now it's being done on machine 6, for instance. And doing this also fixes that machine for all its symbolic small jobs, thanks to this constraint. Okay. So let's say you have this chain. You fix this guy, so you condition on one x ijt for it. So now he gets a fixed machine and a fixed time slot. The other jobs in the chains don't get a fixed time slot, but he does, and they get a fixed machine. Okay, and then once you condition on a job, now you have to control that it really goes to that machine. Okay, so you have a new splitting operation that basically works as follows. So to split this chain into bottom intervals, we do this. We pick a maximum time such that it has some support, and we condition on that. Okay, so I have a picture. So I start with this first interval, and I pick the last time interval that can have some job, and I condition this. Okay, so this guy goes here, and the guy to the left also goes here because, well, he's to the left. Okay, now I do the same for this guy. Okay, so this is a bottom interval. The last thing that goes here maybe is this. So he gets a time interval, and this has to go here because, you know, he's to the left, but on the other hand, he couldn't be here because then I would have picked a different time step for this guy. And so on. I continue like this, and I only do one conditioning per bottom interval, and there's like polylog many of them. So this is fine. Okay, that's one thing. Yeah, so in this way, once I condition on a job, then I always just push them down to the bottom of the recursion, and then I schedule them using conditioning, which again is somehow magical that I can do it because I condition on everything, but I do it in independent recursive calls, so I don't use too many levels. And in this way, I get the correct machine assignment as well. Okay, and then for the second step, which is how do I add the top jobs to a schedule? So in the Levey-Rothvoss algorithm, they use this heuristic of earliest deadline first, and that is fine. But if we just do it here, for just looking at the small boxes as the small jobs, then no, if you just do it like that, you might get a migratory schedule still, because like maybe these two jobs are small jobs that came from the same large job. That would be not good. So for this part, actually, we treat the big jobs together, so as a single long job, and to use to select which job to schedule, use the earliest deadline first heuristic, like Levey-Rothvoss. But now to choose which machine it actually goes to, we choose the machine where it would complete the earliest. So this additional heuristic allows us to get what we need, which is a non-migratory schedule for these jobs. Basically, the hard part sort of is to prove that we have enough spaces in the schedule that we get from the bottom guys to actually put the long jobs in there as one piece, but it's possible. Okay, so let me summarize and also talk a little bit about this harness result that we have. Okay, right. So yeah, so the first result is that for an epsilon and any constant also number of machines, we have an algorithm that runs on m machines that handles arbitrary sized jobs in the model with preemption, but without migration. That is an almost QPTAS, so it runs in time n to the log n to the log n, and it gives a 1 plus epsilon approximation. And moreover, if you have communication delays, then, okay, again, for any upper bound, constant upper bound on the communication delays, we give an algorithm that runs in that time. And C is hidden somewhere in here, okay? All right, now the third thing is a bit subtle. So we have the following problem, okay? So this problem has one machine. It has no precedence constraints, but there are release times and deadlines for the jobs. Okay, so given some set of jobs, each has this interval in which it has to be scheduled, and you cannot do preemption, but you can discard parts of jobs. So you have a job of length 10, then you can just schedule 8 units of it. Okay, the objective here is to minimize the discarded, the total discarded size in a feasible schedule. Okay. So this thing is actually equivalent to a special case of precedence constraint scheduling for just 2 machines without preemption. So in this third model that we had, the most restrictive classic model. Okay. And well, actually, the motivation for this problem on the left is that this is what you get more or less if you try to apply the Levey-Rothvoss approach. Then if you had 2 machines here, then this is more or less what you would have to solve. Okay. All right. So then we prove that a natural LP for this problem on the left, if it's lifted to less than log n levels of the hierarchy, so that's what you would need if you wanted a PTAS. Or if you wanted a PTAS, you would only be able to afford a constant number of levels. So that LP cannot tell if it's possible to discard only epsilon fraction of the jobs, or if you have to discard 20% of them. Okay. And so if you had an algorithm that did the following, if you wanted to solve this problem on the right by going via this reduction and then writing down the LP for this problem and lifting that, then you couldn't do it essentially. Then you couldn't tell using that LP is if the makespan of this thing is less than 1 epsilon times t for some t, or a constant fraction more than t. Okay, so this approach wouldn't give a p-task. Okay, so this is all quite specific. Basically, it's technically really difficult to do something like to prove an integrality gap for lifts, like for hierarchy Shirley-Adams lifts of LPs. So we couldn't prove it for actually the natural LP for the problem on the right. But at least, for what it's worth, we think that the instance that we show this for is kind of the right hard instance. So if someone wants to get p-task for this classic problem of no preemption, then one would have to deal with that instance at the very least. Okay, so now some open problems. Okay, so kind of the main open question, or one of the main open questions is, is there a p-task from this? So this was an almost q p-task or a q p-task. So is constant many levels enough? Okay. And for unit sizes, some experts think that actually m many levels is enough, which would give you an algorithm that runs in time n to the O of m. And this actually works for m equal to 2. So one of the algorithms for unit sizes and 2 machines, like there's this algorithm from 1969, but there is also, what you can do is solve the Shirley-Adams lift for 2 levels, and that also gives you an integral schedule, basically. Okay, this works for 2 levels. Sorry, for 2 machines. Now, is it true for more machines? And is it true also for non-unit sizes? And in the non-preemptive setting, well, our harness evidence is not that satisfactory. So ideally, one would want to prove that the standard LP lifted to less than log n levels has an integrality gap like 1 plus something. So you cannot get a p-task from it. And we would conjecture that if that's the case, then I would say it should be the case on our candidate hard instance. Okay. So the communication delays problem. So here, previously I would say that we know nothing. So there is no non-trivial approximation known if C is large. So recall that we could actually deal with any communication delays, even non-uniform ones, but they had to be small. Okay. But now there are 2 new works in Fox that are independent. So there is a log squared n approximation and independently a log cube n approximation. Okay, but still this is for delays that are uniform. So there's just a constant C. I mean, not a constant. It's part of the input, but you get a C and it holds foreign into jobs, which is not realistic. But people would be really interested to see some techniques that can handle the case of non-uniform communication delays. Like that would be really nice. And then let me list again this simple, one would think, open problems that have been open for a long time. So let's say for 100 machines, is it even in NP hard, the problem with unit sizes? And what can you do for 3 machines? Like for 2 machines, it's in P. What can you do for 3 machines? Like it seems deceptively simple, and people have worked, but we don't know if there is a p-task. So that would be really nice to see. All right, thanks. Any questions?
Yeah, I have a sort of a general question because I don't know much about this area of scheduling. So what other tools are commonly used if you like in this area, in the case you know? Would you like give a brief overview?
Yeah, so people sometimes are able to prove bounds for heuristics. Like the list scheduling is a heuristic. I would say LPs are a really big thing in the scheduling world. So the hierarchies, also our work, like this work from Fox is also based on hierarchies. Although there you just need a couple of levels, and you can actually write down the LP explicitly, at least for identical machines. Yeah, so LPs are a really big tool basically in scheduling.
Which was to be expected because you are such of an expert in LPs.
What's the obstacle for proving the hardness of those problems?
Which ones? Like
the last one you mentioned here.
This, for instance. What's the obstacle? I don't know. Like, it's not clear that you cannot. Like, it's not clear that you can do it at all. Maybe this is in P.
Yeah, stupid question, stupid answer.
I don't know. It could be in P, but yeah. At least people believe that the three machines might be in P. I don't know what people believe for the higher numbers. Yeah, they conjecture P test, but maybe it's in P.
Also, can you comment just a little bit on those Fox papers? How do you deal with the unbounded delays?
Yeah. So in our Fox paper, there is we basically have a natural LP, which again on its own is sort of useless, but then we lift it to some small number of levels, like 5. Basically enough levels so that you can write down, or you can just write it down explicitly anyway. Basically write down a triangle inequality thing on the jobs. And from this you get a metric space of the jobs. And so then from there on, you basically want to cluster the jobs into like intervals of length C on a machine. Okay, so like each mesh, the time horizon of each machine is subdivided into these pieces of length C. And so each can hold up to C many jobs. And basically we make spaces between different such intervals, so that if you put jobs that are dependent into different intervals, then the communication delay constraint will be satisfied automatically. So then basically what you want is that for one time you only put independent jobs in different intervals. If you have dependent jobs, then you want to put them in one interval, or you put them at different times. So this is sort of a clustering problem. It's like connected components even in some sense. And so then we can run some sort of either a ball growing thing, or we actually use a randomized clustering routine, but that is not really necessary to have this randomization. And basically we partition this space into some clusters, and then we assign based on this clustering. So somehow the LP and the, well, I would say the hierarchy solution can allow you to extract some sort of metric that you can work on. I think it's pretty cool. And the other paper, they take a slightly different route. I mean, they also have an LP with a little bit, like some constraints are somewhat similar, but they actually reduce to a version where you have duplication. Duplication means that you can take a job and you can process them on multiple machines, like redoing the work. It's a different model because like normally you wouldn't want to do that too much. But in that model, actually, there are known results even since the 90s. And so they reduced to that, and they prove, which is quite surprising, that a schedule with duplication can be transformed into a non-duplicated schedule while losing only polylog factor.
Okay, thanks.
Sure. More questions?
Okay, I think we have small enough audience that we exhausted the questions from the audience. Okay,
All right.
thank you, Kuba. Thank you.
Okay, thanks a lot.